kind of happy to manage at the moment. It's called a cluster, and it's called the Origins Cluster in Munich-Garching. And the topic is from the origin of the universe to the first building blocks of life. And the idea basically is to understand whether life is already written down in the initial conditions in the storybook of the universe, or whether life is an emergent phenomenon that happened later on, and the universe initially didn't even know that something like that can happen. Now, I need to go into this like this. We are about 120 research groups involved in this, and we basically provide them with funding to work on this. And they cover all fields from particle physics and fundamental physics to cosmology, all the way to biophysics, in order to understand how the universe could evolve and when first life could appear, and is life inevitable, and is the universe fine-tuned, all these wonderful questions. Well, one of the pillars which we fund and which we created is MIAP, and maybe you've heard of that, and would like to advertise it a little bit. It's called the Munich Institute for Astroparticle and Biophysics. It's similar to Aspen. You can apply for a workshop. It runs for 3 to 4 weeks on a certain topic, and then we actually pay the local accommodation, everything. You just have to pay for the trip, and you get an office, and basically what happens is there might be 2 or 3 talks per day, and otherwise you just work together in Munich-Garching, enjoy the Alps, enjoy the lakes, and Schweinshaxen and whatever you want to eat. You know, there are all kinds of things you might want to have. Now, actually, MIAP was first without the B. It was just astroparticle physics, and then we realized we cannot really understand the origin of universe, of life, if we don't include biophysics. So we said, okay, we have to squeeze it in. So we have the little b, and now into it. But the problem is, of course, the biophysicists are a different culture, and they do not really talk about good ideas till they are published. There's much more money involved, and so it's very hard for them to bring them into such an environment where they talk about good ideas. But now it's changing, fortunately. We think we changed the culture a little bit, at least in the environment which we can control. And so we now have several workshops, and you see here a couple of them: interacting galaxies, but also engineering life and so on. And so if you want to apply, please do, and let me know if you're interested. Now, within this workshop, we had last year organized a workshop on self-organization across scales from nanometers, which are biophysics scales, to parsecs, which are astrophysics scales. And the basic idea was to understand what self-organization and emergence means, and whether we also see this if we go to the universe. So just to bring it up, I looked into this. I heard a lot about the biophysics part of it, and I got extremely fascinated by that. Actually, I thought I had chosen the wrong field. I should have gone into biophysics. It's much more fun. But then I said, okay, I can't change this now anymore. So what I can do, maybe I bring a little bit of biophysics knowledge into astrophysics, because it's so much fun. And the idea is very simple. It's the phenomenon of emergence and self-organization, which means you have individual objects, let's say some birds, and they just have local interactions. And through this local interaction, you can get global features, something behaving like a gigantic super bird, if you so want. Another example is basically anthill, where the individual ants don't really know what's going on. The ant queen doesn't give them any instructions, but still the anthill survives for many years. Each individual ant lives only for 1 year, and it behaves, has some kind of swarm intelligence. It reacts to the environment, it stores information, stores food, and so on, knows when there's winter, and so on. It's amazing. And maybe the most fascinating topic or example is self-consciousness, which arises somehow in our brain. But if you open your brain, you look at your neurons, you destroy it. It's not in the neuron. It just simply is an emergent structure that appears when the neurons somehow interact. Now, what is important in this context is that you need an order parameter. Let's call it lambda. And if lambda is too large, let's say it's of order 1 or larger, then nothing happens. You have stability, no complexity, no self-organization. And if lambda is too small, it doesn't work either. You get randomness and chaos. But there's a a kind of critical regime between 0.5 and 1 where self-organization complexity emerges. So there's something even more interesting when you include in this regime feedback, where the individual processes regulate themselves, then that drives actually the lambda parameter to the edge of chaos. And at this edge, you get maximum complexity, you get power law scaling relations covering different length scale and other things, and you get something which is the most emergent phenomenon you can think of. And I thought maybe the same happens when we look at the universe. And I think a great example is actually this here. I think galaxies live at the edge of chaos. When we look at power law, scaling relations, all kinds of features which we see, this is a result of the complex interaction of individual parts which actually then generate that. So if we don't understand this interaction and don't go into any details, we'll never work out how a galaxy works. It might be, we need to figure out what kind of lambda parameter we have here that controls galaxies, where the chaos starts. And we might actually, in the high redshift universe, be in a situation where the galaxies haven't yet found the sweet spot close to chaos, where you get maximum emergence and structure. And that's why you get all over the place, and the galaxy bursts into stars because it hasn't yet found its equilibrium state. And it takes some time to basically settle down. And that's maybe one of the reasons why at high redshift we have feedback-free, or what do I know, evolution, because of this kind of thing. Now, the question is, what could be the lambda parameter in galaxies? And I think it's the 2μ parameter, which basically regulates a galaxy. And as you know, when the stability parameter Q is telling you how unstable a disk is, if Q is too large, the disk is stabilized by pressure, would be turbulent pressure or whatever thermal pressure, then nothing happens. The disk just simply rotates happily, and no structure rises. And when Q becomes too small, you get chaos and randomness. But if Q is in this kind of sweet spot between 1 and 0.5, you get an emergent, very complex multi-scale structure as we see it in the galaxy. And in fact, if somehow there's a way to bring Q to the edge of chaos, then we might get what the biophysicists see all the time, scaling relations that cover very, very different scales, the Larsen scaling relations, or maybe these universal gas depletion time scales, which are everywhere the same wherever we look. So that is something I thought we need to explore in greater details. Now, Q is too general. Q has 3 components, 2 components that stabilize a disk, which is the pressure, the velocity dispersion, and the other one is the shear, epicyclic frequency, V0 over R, and then you have the destabilizing component, which is G sigma, where sigma is the surface density. And the galaxy cannot really control sigma. It's something that is given by the specific angular momentum of the infalling gas and the mass that comes in. The galaxy can't really control V0 because that is given by the dark halo and whatever, how the gas is distributed. But the galaxy can control its velocity dispersion. So I think the control parameter is actually the velocity dispersion with which the galaxy can play to get to the edge of chaos. And here I just show you one numerical simulation of my colleague Manuel Behren. What you see here is a turbulent disk, galactic disk. You don't see the surface density. You see actually where gas converges. These are the red areas, and where gas, the blue areas, and where gas diverges. And it tells you how strong dissipation is, how complex dissipation is, because you actually, in all of these blue areas, you dissipate turbulent energy, and the velocity dispersion is changing through that. And that is something we need to explore. Now, how can we regulate the velocity dispersion in galaxy? Well, you start in a stable regime, and then, of course, you know turbulent dissipation occurs. I just showed you an example. And then the velocity dispersion goes down, and you move into the regime of emergence. That's where we want to bring our galaxy. But actually, it will continue. It will move through the edge of chaos into the regime of randomness, and that's not what we want. So dissipation alone doesn't do the job. We need something else. We need a driver. We need somehow to bring the velocity dispersion up and then it will settle somewhere where dissipation base is compensated by driver. But we have a problem. It could settle here. And then the galaxy is a chaotic system. Or it could settle here, that is better, then we might get an emergent structure, but it's not necessarily at the edge. But it could also settle here, and then you have stability. So that alone can't solve the problem, because you can, in equilibrium, if you have some turbulent driver you can think of, can end up anywhere on this kind of line. So you need to be a little more clever. And the idea had been that it's basically gravitational instability itself that drives turbulence. Because then there's a difference here. When you go through the one into the emergent regime, then you get gravitational instabilities, and it continues all the way to the very small values of Q. And the idea has been, when you get to smaller and smaller Q values, and the gravitational instability becomes stronger and stronger. And suppose you start over here, then due to the instability, you drive an enormous amount of turbulence till you end up in the emergent regime, and vice versa. If you start up in the stable regime, then dissipation dominates, gravitational driving is unimportant, and then you automatically move into the regime which you need. And I have written several papers. I've written a paper with Avichai, which is highly cited, and I tell it's all garbage. Unfortunately, it's all wrong. And I now completely, okay, Avichai looks at me, okay. Okay, let me tell you why I think it's not really working. Well, suppose you start here with a very, very small value of Q, and look at what happens with the velocity dispersion when the disk becomes unstable. And you see it here. The disk actually begins to fragment. Q is so low that you are in the random or chaotic regime. So any little density fluctuation which you have in this rotating disk will grow. And the deeper the potential well, the more gas falls into this potential well. So what you get is lots of little clumps, but they don't really interact. And there's no self-regulation. There's no global structure, not anything emerging at all. It's a mess of little clumplets. And now when you look at the velocity dispersion and Q, then indeed Q rises. It's almost zero initially, and then it rises. Why does it rise? Well, you get non-circular motion due to the local collapse. It's all collapse motion. But it's not turbulence, because turbulence is a pressure term. It's something that has to act outwards. What we see is just simply everything falling together. You can't stop the collapse by the collapse itself. And then you get into a regime where Q oscillates around 1. Why? Because you have all these little clumplets now moving around like bullets, scattering. You get a globular cluster, basically a flat globular cluster. It virializes, but this is not turbulence. This is not self-regulation. It's nothing like that. So to me, it means that gravitational collapse is not actually basically preventing and moving the system into the regime of emergence. It just doesn't work that way. We can calculate the Q value formally, but it makes no sense because the random motion we see is collapse motion, and this is not working like pressure. And it reminds me of a nice story in Germany about Baron Munchausen. You know about this? This is a guy who violated physics all the time, and he got once into a swamp with his horse, and then he tore himself out of the swamp on his own hair. And that's basically what we see here. Gravitation collapse cannot prevent gravitation collapse or slow it down. It simply doesn't work. The potential energy released goes in the PDV work in the sedated way. That's what it is. Now you might say, okay, maybe we should start in the stable regime and then let the system become gravitationally unstable. And maybe in that case, gravitation collapse can do the job. And here's a simulation where we start with a hot disk. The disk then cools slowly, and then the disk becomes gravitational unstable and becomes tumor unstable. What it will form is rings. First, because tumor instability is a ring formation scenario. It's an axiomatic thing. And then later on, these rings of dense gas break up into clumps. And you might say, okay, this is now turbulence. But it's not at all. It goes through a phase of emergence, but then you get again clumps. You get more and more clumps, and everything converges into clumps, and you get the same result we got before. You get a system of points moving randomly around, and not at all any turbulence. Forget about this little bit of gas in between the clumps. At the end, you have holes and clumps moving around. So gravity also doesn't do the job if you start with a stable disk at all. And again, you can look at the 2μq, it's of order 1, but it's only actually, you see it here from the ring formation. Q gets of order 1 because everything collapses into ring, some radial flows, and then you have clump scattering, and then actually this realized system has a Q even larger than 1. So I think the solution must be stellar feedback. I think the way to regulate the galaxies and bring them into this regime is by forming structures of gravitational collapse. But in order to rejuvenate the galaxy, you will always have to blow the structures apart. And the only way I know how to blow them apart is by stellar feedback and not anything else. So at the end, you need the stars, and the energy has to come from the feedback and not from gravitational collapse or something like that to do this. And so I think what happens is, if you have no gravity, then basically the stellar feedback and the kinetic energy dissipation will bring your system anywhere along this line. It will not select this region. It will be a turbulent box, what you basically see. And I, of course, understand why it doesn't select this region, because 2μq doesn't work, because G is 0, so that doesn't work. But when you add gravitational collapse, then actually, basically what happens is that you can get hierarchical structure formation, this regime. It could well be that here you have too fast a collapse, that the galaxy will basically crank up star formation, so it will automatically bring it into this regime. I don't really know whether we can actually theoretically generate galaxies that could basically live in the chaotic regime. Maybe at high redshift they do this. I don't really know. So that's something which is going on. And then I think we still need the feedback to bring them to the edge of chaos. And this feedback happens due to the fact that basically star formation is driven by the collapse itself, but star formation through feedback destroys the collapse structures. And this kind of feedback loop at the end might lead to galaxies that end up over there. Now, this is just an idea. I do not really know whether Q of 0.5 is the sweet spot where you go from emergence to chaos, and whether galaxies always end up in this regime, and what kind of implications this has with respect to feedback and with respect to scaling relations, whether we go to high redshift galaxies all over the place, sometimes here, because they haven't yet figured out what emergence means. So these are things I don't really know, but I think we can learn a lot from the biophysicists. If you have a chance to have some biophysics people at your university, invite them for a colloquium. It will be a lot of fun. Thank you very much for listening.
So Andy, my friend, you know that I have loved every talk that you've given in the last 6 years at this conference. But so I spent 30 years as a biophysicist, and I don't think you, maybe it was a tongue-in-cheek characterization of biophysicists. And biophysics is a big word, and there's some biophysicists that would fit that characterization. But there are a lot of biophysicists that are primarily physicists studying biological materials. And to give you, you don't have to believe me, Reinhard isn't here, but I did 2 years of biophysics with Reinhard's father in Stuttgart.
Wow. Mm-hmm.
And if you want to know whether he was a good physicist or not, ask Reinhard. So I'll have to write a proposal to come to Munich.
Please come over. Yeah. Thank you.
Thank you, Andy, for a fascinating talk. I wanted to ask whether, if you include magnetic fields, that they work in a way that enhances reaching the chaotic point. Because I can imagine that as things get messed up, the pressure increases. So there's a little bit of feedback. They also have long range as well as short range conductivity. So what do you think about that? Is that totally crazy?
No, it's not crazy at all. It's absolutely correct, but it's a very tough question, of course. But I agree with you. Magnetic fields certainly change this kind of critical Q value. It's a magnetic Q value which we now have where the transition to chaos can happen. And it, of course, leads to much more multi-scale structure than before. And even in the case of pure gravitational collapse, with magnetic fields, we might get much more turbulence than we get in this very simple simulations. And that's certainly something interesting to investigate. Computational tough. Yeah. No, and from the brain. I mean, it's already, without magnetic fields, it's already hard to understand. And turbulence with magnetohydrodynamical turbulence is even tougher. I mean, but it has to be done. At some point, we can't work without it anymore. Completely agree.
Yeah. Andy, thank you very much. Very inspiring. I was impressed by the experiment in which you start from the stable disk and then you have these rings and so forth. So actually this is not really, even if you have Q larger than 1, this is actually a metastable state rather than a stable state. So can you explain what's happening?
So what we are doing, we have first gas that is hot at 20, 30,000 K. Then we cool it down. And then basically when it goes below QQ1, then you get all the structure forming. Yes.
If you could keep the gas at that temperature, it would be truly stable. So it is metastable on the scale of the cooling time.
Sure. Yes. Here we don't have any source of feedback. So I just wanted to see whether turbulence alone can be driven by gravitational instability. And what I see, it's a one-way street. It all goes down to a very small real Q value. If you don't consider this as this random motion as turbulence. And so you need the feedback now to blow this apart. And then you get something which mimics a real galaxy. But my point was to make that turbulence can be never driven by gravitational instability over a long time scale. It only temporarily exists like that. We always need the feedback at the end. The stars have to do the job to drive the turbulence.
Next speaker, please.
And your analogy with biosystems is very interesting. I have no idea if it holds water or not, but it's very exciting. But about the astrophysics, one missing piece in driving turbulence is accretion. Remember that our disks are not isolated. They live in a universe with a lot of stuff going on. Especially the most emergent disks are the redshift 2 kind of disks, which are very violent and clumpy, etc. And that's where the accretion is also important. Yep. I think the next talk will address this in some ways. So you must add the accretion as driver of turbulence into the game.
Good. I agree.
The other thing is about gravitational instability. It's not only the collapse to local clumps that you have to worry about. It's the energy you gain by contraction to the center of the galaxy, which by gravitational torques may or may not drive turbulence. Another thing to worry about.
Yes, we are working on this, and we don't get the radial flows yet, which we tested the torques. We don't generate enough torques to drive radial flows inwards to compensate for the dissipation of the turbulent energy. Just simply two different processes. Torques bring the gas in, but the energy you release to drive turbulence is a completely different thing, and it doesn't really work out at the moment. But you're right, it's something to explore.
We need to continue. We thank Andy again.
Thank you.